So in this video, we're going to look at more optimization problems, but in these problems, you're not going to be given the equations for like revenue, profit, demand. So instead, you will have to come up with them. So we're going to look at an example, and then I have a lot of extra examples from the packet that I have videos as well that you can watch if you still need help with this. But what we're going to do is you're going to read the problem carefully, draw a picture if possible, and then assign variables for what you're trying to find. Most of the ones we're doing won't have pictures because it's revenue, profit, and cost. But if you took a different calculus class and you were doing something with maximizing, minimizing area and perimeter, it's helpful to draw a picture for those. Then you're going to write an equation for what you're trying to maximize or minimize, and that's called the objective function. If there's constraints, you'll write another equation based on the constraints. Then you're going to get the equation you're trying to optimize in one variable, take the derivative and find critical points, and then verify that the critical point is a max or min. Most of the time we will do the second derivative test for these just because it's faster. The only time again that the second derivative test cannot be used is if you have to check endpoints. So if they give you a closed interval. Okay, so let's look at one where they actually do give us the equations, but what you can see is you want to find the maximum of Q equals XY if X plus Y equals 2. So I have two different equations. And the issue is if I look at Q, it's in two variables, X and Y. And for now, we cannot find the max or min if we have two different variables. You will learn that in the end of unit 3, but right now we don't know how to do that. So if I want to maximize Q, Q is called the objective function. That's whatever I'm trying to maximize or minimize. And then the other function, this X plus Y equals 2, is called the constraint. So it's another equation that has to be true in this problem. And the constraint lets me get Q in terms of one variable. So what I can do is I can solve for X or Y in this second equation, and then use that to substitute in for the variable that I solved for. And then it's in one variable, so then I can do the process of optimization to maximize it. So it really doesn't matter what we solve for, but we more often have things in terms of X. So that's what I'm going to do in this case, because neither one is easier to solve for. So if I get this equation in terms of X, I'm going to get Y by itself. So I would subtract X from both sides. And that would give me 2 minus X. And then for equation Q, to get this into one variable, I'm going to substitute in 2 minus X for Y. And now I have it in terms of one variable. I'm going to distribute so I don't have to do quotient rule. And then I'm trying to maximize this. So we do our optimization process, which again is where we take the derivative. We set the derivative equal to 0. And we solve for our variable. So if I solve this, I'm going to add 2x to the other side, divide by 2, and I get x equals 1. So this most likely is my max. I'm going to verify it's a max by doing that second derivative test. So the second derivative is -2. Okay, so even if I plug in my critical point of 1, it's still -2 because there's no variable, which means my original function is concave down and the critical point is a max. So x equals 1 is where a max occurs. And then let's make sure we answer the question. So if I go back to the question, it says find the maximum of Q. So I actually need to find the value of Q because that's what the maximum would be. So I'm gonna plug one in. There's two ways to do it. You could find Y and then plug it into the original, or just to save us a little time, we can just plug it into Q because it's in terms of X. So we know that Q is 2x minus x squared. And then we're gonna plug in, find Q of 1. And that gives me 2 times 1 minus 1 squared. So that's 2 minus 1, which is 1. So the maximum of Q is 1. And so that's just an example of one that has more than one variable. Now, in this class, we're not going to have that as much. What we're going to have is these problems like this, where we're trying to apply like revenue, cost, profit functions to real life examples. So this problem says the average ticket price for a concert at the Opera House was $50. The average attendance was 4,000. When the ticket price was raised to $52, the attendance declined to an average of 3,800 persons per performance. What should the ticket price be to maximize the revenue for the Opera House? Okay, so for these problems, what we want to do is we're trying to maximize revenue. Okay, and just remember that revenue is equal to X times P of X, where P of X is the demand function, the price demand function. And this problem will give us a linear function for the price demand function. So when we do this, P is your price and X is, in this case, the number, the average attendance. So what we're going to do is we're going to use this information to write a linear function for the price demand function. And then we'll plug it into this formula to find the revenue function equation. And then we'll use our process of optimization to find the maximum. And we need to make sure we find the actual ticket price. So we do have to find P of X at the end. So what we know is our X is average attendance. So what we're going to do is we have two values that we know. We know that when the average attendance is 4,000, that's my X value. The P of X value, or the Y value, would be $50. And then it said when the ticket price was raised to 52, we know the attendance declined to an average of 3,800. So this is 3,800 and this is 52. So for these problems, we always assume that they're linear, that the change will be the same each time. So each time that the price per ticket goes up by $2, the attendance is going to go down by 200. And so what we're going to do is we're going to use these 2 points to find a linear equation for P of X. And then we'll plug that into our revenue function. So when we want to find a linear equation, again, the format is usually Y equals MX plus B. Now in this case, we're going to use P instead of Y to indicate my function for our price demand. So our price is equal to MX plus B. So we first need to find the slope. The slope is, again, the Y2 minus Y1 over X2 minus X1. So we get 2 over negative 200. Okay, and you can either leave it as a fraction or a decimal. It's gonna be negative 0.01, or you can do -1/100. Either one is fine. Okay, so then we have to find our B. You may use point slope or y-intercept form. I'll just do y-intercept. So we have P equals the slope -0.01x plus B. I need to find B, so I'm going to plug in one of these points. We'll just do 4,050, it doesn't matter. This is my X, this is my P. So we have 50 equals -0.01 times 4,000 plus B. We're going to solve this. So I get 50 equals -40 plus B, add 40 to both sides, and I get 90 for B. So my price equation is -0.01x plus 90. Okay, so that's my price equation. My revenue is always X times that price demand function. So R of X is X times this equation. And then we want to maximize R of X, which means, again, that we need to find the derivative and set it equal to 0, and then make sure that that X value is a max. So again, so that we don't have to use product rule, if it's easy to distribute, or you can distribute, you usually want to, so we're going to distribute that X. We're going to take the derivative. We're going to set the derivative equal to 0. So we get -0.02x equals -90. And we get the price, the average attendance to be a max at 4,500. Okay, we're gonna verify that it's a max just to make sure. So we take the second derivative. Again, the second derivative of this is just a constant of -0.02. If I plug in 4,500, I just get -0.02, which means, again, it's concave down. The critical point, again, here is where the tangent is horizontal. And so R is concave down, and X equals 4,500 is where a max occurs. So this is my X value, but again, always go back to the question, because usually they ask for more. So it said, what should the ticket price be to maximize the revenue? The ticket price is this P of X. That's the price demand function. And again, P of X is the ticket price in this case. So to find that, we are going to take our X value, which we found, the 4,500, and plug it into our P of X equation that we found, this -0.01x plus 90. So I have -0.01x plus 90. We're going to find that price at the attendance of 4,500. I don't know why my pen sometimes randomly changes color. So I get -45 plus 90, which gives me $45. So we're finding that the price that maximizes revenue is $45 with attendance of 4,500. And this is going to be a lot of the optimization problems that you see. So you're going to have to come up with your demand function using that linear relationship. Then write your revenue as X times the demand function, take the derivative, set it equal to 0, find the point, and then just make sure you're answering the question. So please let me know if you have any questions about optimization.